Hello everyone, good evening. Somebody has asked to increase the live session. Yeah, I'll speak with the professor. If he can do that, we'll definitely do it. I hope you have gone through all 3 weeks so far. So we'll jump to the fourth week of the content today. I'll first brief the contents of the fourth week a little bit, and then we'll go to the problem solving session. In between, I'll ask some questions as a surprise quiz, and you can answer in the chat box. I hope I'm audible. Can anybody confirm it? Yeah, thanks. Fine. We'll start with week four. So, week four is all about time domain analysis. And in week one, we have seen some introduction about a control system which involves all the open loop, closed loop, how we will represent a system, how to model a system. So that modeling will take a big part in this week two and three using the Laplace transform. I think week three would include Laplace transform. So before introducing Laplace transform, we would have started with how basic thing before that, what this week two would have covered. It's time and frequency domain characteristics and introduction to Laplace have been done here. Laplace introduction. And here we have seen types of systems. So types involves all the linear, non-linear, periodic, aperiodic, static versus dynamic and everything. Now in week four, we are covering time domain. Why specifically time domain is in control system, we can broadly classify the system using two different representation. One of the representations are time domain analysis and frequency domain analysis. Some systems are easy to analyze in time domain, some are easy to analyze in frequency domain. So this will be covered before week 5, half of the mm, prior weeks, and this will be covered after week 5. So apart from this classification, we can also discuss or classify the systems into continuous systems or discrete systems. Both are, these two are not related to each other but different types of classifications. This is one versus one, but this is another versus another, right? There can be a system that is continuous that can be represented in time domain. There can be a system that is discrete that can also be represented in time domain, vice versa, in also in frequency domain. So these are different types of representation where one whoever is feeling comfortable with which domain, they can go with that. For example, time domain has some advantages and also some disadvantages. If I want to say, when a system is given an input, there is an output that we know, but what happens to this output with respect to time? That's what that this time domain analysis answers these questions. So it answers how fast the system behaves, whether it oscillates or overshoots, what is the behavior? Basically, what is the behavior of the system? How the system behaves? And does it settle, or it keeps oscillating? So these are same question, but it again indirectly answers that does it has a desired value. If it settles, it has a desired value. If it is not, it won't have a desired value. So these are all the criteria a time domain analysis for a system will help us to understand. On the other hand, time domain analysis is a little complex when compared to frequency domain, because in frequency domains whatever we are doing it here in convolution can be done in multiplication in frequency domain, as we saw in the Laplace domain, right? So that is another way of seeing the same system in different perspective, right? First we will see what are all the concepts it is there in time domain analysis and how we can work on that particular specifications or any criteria. For example, the same system I'm taking. If I take a system and I'm giving an input kind of this or a step input kind of this, and I'm getting a output like this. For example, I'm taking some random outputs right now. So this response can be of, and again two different types. One is natural response, another one is forced response. So this forced response or natural response corresponds to the zero input response. So it's a autonomous system we used to call. We don't need any other external input to activate or run the system. It itself has the ability to keep on going without any external input. So it is called a zero input system or autonomous system that doesn't need any external input. Forced response involves some amount of input from our user side. So when we give some input, and if we get some output, we call that as a forced response, external input, I'm saying, right? This is because of stored energy. It activates because of the stored energy. This needs an external input as an energy. So if I take a fan, I'm switching on, I'm giving voltage as an energy, input energy, and I'm getting speed as an output, and it's mechanical output where we get air, flowing air from it. If the speed is increased, the flowing air will also get increased. You will feel very good after reaching the highest speed. So if I turn off the fan, still the fan used to rotate for some times, right? It's not like when I switch it off, it suddenly stops. It has some stored internal energy. The capacitor should degrade from its stored capacitance that pushes the fan to further limits. So the response you are getting when the switch is on, the moment you turn on the switch until you turn off, it called as forced response. Once you turn off, the response you are getting after that can be considered as a zero input response. It's the example system I am taking. There are systems that doesn't need any inputs. For example, oscillators that doesn't need any inputs. So it has their own stored energy. They can keep on producing the output responses. So the explanations or expressions for these circuits have been mentioned in the presentation that you can go through. And if you have any doubt, please stop me then and there. We'll discuss about it. Right. And these are all the classification in terms of responses. I'm going to say another classification in terms of behaviors. So this is based on responses. In terms of behaviors, this can again be classified into transient and steady state. So any system, if you take, I'm going to draw only the output response, assuming there should be some input, right? These are some input. Any system has two different types of behavior. And the moment when it starts, there will be a higher oscillations or a peak, we used to call. And then at some point of time, it used to settle. If it is a stable system, this settling behavior works for only the stable system. If you take an unstable system, this is not going to happen. It's not going to settle anywhere. So you cannot study the steady state behavior for a unstable system, right? I'm Hereafter I'm going to speak only about the stable system. If it is a stable system, this can be classified into two different scenarios. This considers to be transient behavior. For some times, if it keeps oscillating, this is called as transient behavior. Once it settles, we call this as a steady state behavior. Okay, both of the behaviors tell us more about the system state or the system's characteristics. Okay, so if the transient is more and it takes longer time to settle, then we need different types of control. Or if the transient is very less but it quickly settle, it is a very good system. The control effort needed is very low. So based on that, ultimately we want to design a control input, right? That's the topic of the um, this paper, control systems. So you want to design a control criteria where you want to control a system's output, a system output. So if the based on this transient and steady state behavior of the system, we'll get to know what type of control we have to design. So if I take a output, for example, if I take a RL circuit, let's take, okay, from forced response, I'll try to. You know the expression for the forced response, right? If not, please revisit the slides. It has from the basics. We don't have much time to cover all those things. C power minus T by tau. This is the expression for forced response in terms of a RL circuit. Taking an example of an RL circuit. So here, if you see, this term e power t by tau represents the transient term. So this tells when you turn on the system, suddenly at that moment how the system is going to behave. That is the transient term. So this term V naught by R, it's going to tell you the steady state behavior. So after some time, when the system settles, assuming it's a stable system, when the system settles, where it is going to settle, that is being calculated using this V naught by R. So whatever the system resistance is and whatever your input is, based on this, the system is going to settle at a value V naught by R, right? Okay. And there are systems, based on order of the systems, it is classified. Order means what is the maximum, highest degree of the denominator of your transfer function. Okay, for example, if I have s plus 1, then this is first order system. If this is a square plus 2s plus 1, second order system. S plus s square plus s cube plus. What is the order of the system? Please unmute and answer.
Third order.
Third order system, right? So based on this, based on the highest degree of your denominator, the order of the system varies, right? Give me a minute. Right. Okay. So first order system has a representation like this. For example, I used to call x of s, let's take k by tau s plus 1, where tau is the time constant. right? So when you find the solution for the system, uh, it will tell you 1 minus e power minus 1. So this gives me 0.632. Is roughly the value is 0.3632. So this is why we used to call time required for the system to reach the final value. Here is 0.632. This is why we used to wait until it reaches 63 percentage of the overall value. If you would have listened to the lectures, you would have calculated. So the time that we used to wait until it reaches the 63 percentage of the overall final value that we used to calculate, right? This is the reason why we are interested in that for a first order system. So naturally it gives us this values to calculate the final value. What else we would have seen in this? Damping. Okay, I'll come to damping. Different types of damping has been just represented. Okay. And changing it. If I have a output response for a stable system, and this is my response, I will take this, we call it as peak. The time taken to reach this peak is TP. The maximum value we call it as peak, but the time taken to reach this peak will be called as TP. So until this point will be TP. And the overall value it takes, for example, this is my steady state value 1. It's supposed to reach here, but it overshoots over that my steady state value 1. So the value that it overshoots, that percentage we used to calculate as peak overshoot. For example, if if I'm supposed to settle at 1, if I'm supposed to settle at 1, but instead I settled at 1.5. So the difference between this is zero point 0.5 divided by 100. That much of percentage I have overshoot. That we used to call it as MP, peak overshoot value. Okay. Right. And the time that have taken to reach, I don't know, it is very much delayed. The time it has taken to reach 63 percentage of the overall value that we used to call it as rise time, TR rise time, TP peak time, time taken to reach the peak, time taken to reach the 63 percentage of final value, as I said before in here in this example, right? And TP is to reach the peak value, right? And there is a time called settling time. The time taken to settle or go to the final value, desired value we used to call. So final or desired value or settle time to settle, that we call it as settling time. Apart from this, what else we have? We have delay time, right? Another term is called delay time, and this is the time taken to taken for the response to reach 50% of the final value, not 63, it's 50% of the final value of the first instance itself. Right, this is called as delay time. So for every criteria, the parameter, there are formulas or expression used to call. So for problem solving point of view, I'm going to write it here. You know how it comes and how to derive this expression which is in that presentation. Or if you need separate session for this, then we can arrange it. Right now, I have planned to do the problem within this 1 hour based on this. That will be helpful for your quiz. So this is rise time, cos inverse. It can also be represented like this, omega n root of 1 minus zeta square. I hope you know about what are all the terms that I have been written here, right? If you don't know, please ask me what are all those things.
Ma'am, please explain that.
Okay, right. I'll explain. Fine. So this we call it as zeta, and this is omega n is natural frequency. Sometimes it looks like a tau. That's why I'm mentioning zeta. Zeta is the damping ratio. Okay, and omega d is the another frequency criteria. So I will explain what everything. I have explained the first order system, right? First order system will look something like this: k by tau s plus. This is tau. It's not zeta. Tau s plus one, where tau is the time constant here. It represents at which time the system is going to settle, or how fast the system is going to settle. For first order system, only this knowledge is enough. For a second order system, we need little more information. For example, a second order system would look something like this: a square plus 2 zeta omega ns plus omega n square. Right. So this is the standard representation of your second order system. Most of the system real time example, or most of the systems we are going to see in this course is this second order system. For example, a mechanical system, MBK, we used to call mass spring damper systems or suspension systems. Another best examples are robotic systems, aircraft dynamics. So these are all the systems. These systems can come under second order, or we can approximate it under second order system, because second order system is the most known, or it's easy to analyze its characteristics when it is represented in certain way. So this damping frequency is the important term that I have written it here, zeta and omega. So this zeta tells us how fast the system is going to converge towards final value just by seeing the system, or just by knowing the characteristics of the system. For example, this zeta can hold values at a 1 generally. So most of the systems will most of the systems zeta would come under 0 to 1. That is the value bound for it. And there are systems lesser than this and greater than this, that we will come to that later. So let's consider a system that zeta comes under 0 to 1, where 0 is the least value and 1 is the maximum value. 0 tells there is no damping. For example, if I have a door for a AC room, I have no special provision in my door. I will just keep my door open and let it be open if there is no damping. Right. Wherever I keep my door by hand, it will be there. It will just stay there without any damping. That's a no damping system, where zeta is nearly equal to 0. For example, if I have zeta equal to 1, I have a spring that attached to the door frame and the door. So when I leave the door, when I just open the door, and the spring will help the door to come back to its position so that the AC will not be wasted. So this, I can say this is a maximum damping 1. Let's consider if I equate this to the example. What about the 0.5 damping here? So somebody put anything in the chat. Eh, no, income messages. Live stream the session. Okay. Okay, we will upload the recording, right? You can watch that recording later also. My screen is visible, right? I
Yes, ma'am.
okay, okay, fine. Okay, what about this point 0.5 damping? Point 0.5 damping is half of the damping I used to get until I, if, for example, if I have point 0.5 damping in my door, it will take much more time to close the door. So that's what I said. This zeta determines how fast your system is going to converge to the final value. Omega n is the natural frequency, at which frequency it's going to converge. That is the idea we will get out of omega n. So these terms we will use to calculate the nature of the system. For example, this is the formula for TR. Back to the formula, TR tells pi minus theta divided by omega n, where theta can also be elaborated into pi minus cos inverse of zeta. It's another term. No, there is no special mention
Ma'am,
for these
pi
things.
minus theta by omega.
Omega d, damping
Okay.
frequency it is.
Okay, ma'am.
And there are another formulas. Peak time. For peak time, the formula would go something like this. There is no theta won't be minimized from that pi. Overall, one frequency we will calculate, no, 3.15. It will just be pi by omega d. That can also be written as pi by omega n, where omega d is omega n minus zeta square. And that we used to call it as damping frequency. And delay time. This is rise time. Peak time can be calculated for any system using this formula. Delay time can be calculated using this formula. Delay time TD is equal to 1 by 1 plus 0.7 zeta divided by omega. Similarly, I have written rise, peak. What else I'm missing? Settling time is there, no? Settling time can be differentiated into two types. One is 4 by zeta omega n. This is for 2% tolerance. In the questions we will ask for which percent tolerance. If it was not asked, then go with the 2% tolerance. For 5% tolerance, it is 3 by zeta omega n. This for 5% tolerance. Default, please use this formula. Otherwise, if the tolerance is given, choose the appropriate formula for that. This is settling time. What else is missing? That is peak overshoot. This is really
Ma'am,
important thing.
T is equal to.
Okay, I will write it more clearly. 4 by zeta omega n. This is 3 by zeta omega n. Is it clear now?
Yes, ma'am, clear.
I will write it slowly. Okay. So peak overshoot is e power zeta pi divided by 1 minus zeta square. Whole is in the power. Okay. The minus will also be there. Please be aware while writing this formula. Most of us are leaving this minus. So it is the formula for finding peak overshoot is e power minus zeta pi divided by 1 minus zeta square. This many into 100. If you multiply it with 100, you will get it in percentage. Otherwise, you will get it in point or something. If the question asked in percentage, just look for the values or question thing. Just multiply it with 100 and write your values, right? If it is asked in percentage, just multiply it with 100. Otherwise, leave it as point itself. Okay, so these are all the time domain specifications. So this we are going to use to calculate the specifications of any systems, and that we are going to solve problem right now. So I'll
Ma'am,
take
can
some
you repeat the delay time?
delay time. Ah, delay time is used to calculate. It's just the different concepts. Like for example, if I give an input to a system and I'm getting an output, I might need different types of information, right? If I want to know what is the value or what is the time taken to go to 50 percentage of the final value, then we call that as a delay time, and we use this formula. This formula. Otherwise, if I want to know what is the time taken to reach from 10% to 90% of the final value, then I will go with this rise time formula. Otherwise, if I want to know what is how much time it takes to reach the peak of the system, peak of the response, then it is peak time. How much time it takes to reach the final value or to settle in the final value, that is the settling time. It's a straightforward thing. Whatever you want to know, we are naming it in terms of that only. So we will solve some problems. I think that will help you to understand it better. If not, we'll come back here again. Okay. And
Ma'am, please explain last point. That is, this is last formula.
settling time you want to know. Settling time, that I hope that I have explained last. So settling time is a time taken to reach the steady state value or the final value of the system. If I turn on my fan, if it goes to 230 rpm first, and then at last if it settles to 200 after 5 minutes, then 5 minutes it's my settling time. And when it reaches 230, if it is 1 second, then 1 second is my peak time. So that's how we calculate.
Okay, ma'am.
Okay, first we need to know how to calculate theta, omega, and these are all the basic parameters. No, that's there in the formulas. So first we'll do problem based on that. Then we will try to find that rise time, peak time, and everything. If I take a system, second order system, y of s divided by r of s, 64 by s square plus 8s plus 64. This is my question, Q1. Okay. So I want you to calculate zeta and omega n. First, if any question has been asked like this, compare it with the standard second order system representation. That goes something like this: omega n square divided by s square plus 2 zeta omega n s plus omega n square. These two are same, and 2 zeta omega n is a middle term. S will be here, s square will be here. This is the standard second order system representation. Okay, fine. When I compare these two equation, what I will get: omega n square equal to 64, 2 zeta omega n is equal to 8, right? You are with me, right? Everybody understood this thing, this point. I hope so. If not,
Yes, ma'am.
okay, fine. Now from this, can we find omega n square is equal to root of, sorry, omega n is equal to root of 64. It is 8. Now omega n equal to 8, that we found. Substitute this in this formula: 2 zeta omega n equal to 8. 2 zeta omega n is again 8 equal to 8. So 8 and 8 will get cancelled. 2 zeta is equal to 1. Zeta equal to zero point 0.5. 1 by 2, zero point 0.5. So I have found zeta damping ratio. So this has half damping. The system has a half damping until it reaches the full. Okay. So damping ratio zeta equal to zero point 0.5. Omega n natural frequency is frequency at which this convergence is happening is how much it is: 8 radians per second, something that we found wrong. Now just update this or substitute this in the formula one by one. For example, if I asked you to find the peak overshoot, how will you find? You have to write the formula for the peak overshoot: e power zeta pi divided by root of 1 minus zeta square. E power minus zeta is zero point 0.5 pi divided by 1 minus, 1 minus it is, right?
Ma'am, what symbol you are giving? Peak
Zeta.
overshoot?
Zeta.
No, no, peak overshoot
Oh,
here.
MP percentage it is. Peak overshoot.
Okay, okay, okay.
MP percentage. Percentage in the sense I'm going to multiply it with 100.
Yes, ma'am.
Okay. Wait, let me close this and reopen it. It is getting stuck. Okay, fine.
Ma'am, please upload graded and practice assignment solutions.
Solutions won't be there. You have to solve by yourself, and if you have any doubts, you can come to the live session and ask with that particular question. But you have to solve in steps. We can help you with the steps. We can help you with
Okay,
the
ma'am.
questions. There is generally we won't like give
Ma'am,
over
after
that
ma'am,
question.
after submission, you can give the answer. Or
Professor didn't explain like that because professor won't encourage just seeing solution and understanding this. He wants you to solve by yourself, and if you get stuck, and we are there to help. We both instructors would help you.
Ma'am, where we have to message like mail in mail or in um, discourse.
This time only the discourse has been created. Previously, we used to have it in the Gmail chat box. So we are not aware of it. Later, around 2 3 days before only, I get to know that there is one forum like that from the base degree team. So some people have mailed me that there are questions in discourse and that has not been answered. I'll sit and answer those questions in discourse. We'll communicate in discourse itself.
Ma'am, what's your ID in discourse? Ma'am, means if we want to mention you, so then what's your ID?
Okay, let me check one minute. Same Vasumathi Raman, if you type it, it would come, I guess. It's Vasumathi underscore. Can you hear me?
yes, ma'am.
Yes, ma'am.
So it's Vasumathi underscore R at the rate study. Everything small. VASUMATHI underscore R at the rate study.iitm.ac.
Ma'am, are also small letter.
Small, small. Everything small.
Okay, ma'am.
Okay, like we don't have much time, so I'm going to rush this. So this is 0.55 divided by 1 minus 0.25. So if you calculate this
Ma'am,
answer,
there is a root.
root, sorry, sorry. That's right. Sorry. Okay. If you calculate this, yeah, you will get your peak overshoot. Just calculator calculation. So I'm leaving it here. So we will move towards the next thing. So one thing we found, peak overshoot we found. The next thing is peak time. So at what time it reaches the peak? Maximum value of this response. That is pi by omega d. Where omega d is omega n root of 1
Sir,
minus.
ma'am,
Ah,
ma'am, peak overshoot will be the value in percentage or
in
without
percentage.
percentage?
In percentage. It's generally in
Oh,
percentage.
okay, ma'am. Okay, ma'am.
That's why we are multiplying it with 100.
Okay, then if it that overshoot value is if overshoot value is given in the problem,
Mhm.
then we have to direct put the formula equal to that value. If
Mm.
overshoot value, peak overshoot value is
No,
given, any
I
problem.
yeah, I will tell that 25 percentage is my peak overshoot value. Then you have to take it as 0.25 for calculating all those things.
Okay, okay. Okay, ma'am. Okay, ma'am. Understood.
Because peak overshoot, how we'll calculate percentage, MP divided by 100 is the percentage, right? So I'm going to
Yes.
multiply this 100 to this right hand side value. That's why we are multiplying 100 here.
Yes, ma'am. Okay.
Okay, and this is zero point 0.5 square. Again, if you calculate it using calculator, you will get the peak time in seconds. Please don't miss the units. For peak overshoot is percentage, everything else has seconds. Similarly, if I ask you to find the rise time, it is pi minus theta divided by omega d, same, where theta is indirectly represents cos inverse of zeta. Zeta also you know. Omega d is omega n root of 1 minus zeta square. Pi minus cos inverse of zero point 0.5 divided by omega n is 8 root of 1 minus zero point 0.5 square. This gives me rise time. Settling time is for 2% tolerance. I am going to calculate 4 by zeta omega n. 4 divided by zero point 0.5 into 8 will give me the settling time, right? So this represents, just repeating it, this represents time taken to reach the maximum value TP. TS is time taken to reach the final value, time taken to reach from 10% to 90% of the final value or peak time I have given. No, peak overshoot is maximum overshoot from the settling value. For example, if one is the nominal final value, if it goes to 1.25, then 0.25 is the maximum overshoot. Fine. Now you know all the terms which are we are very familiar with this. Now we are going to move towards the steady state error, which is another very important topic. It carries a lot of marks. Now I told you, if this is, oh, before that I have to tell about the damping, right? So we studied two different specification. One is zeta damping ratio, another one is natural frequency. So while explaining that, I forgot to tell this. So damping ratio, based on the nature of the damping ratio, we are classifying this into four different types: undamped, underdamped, critically damped, overdamped. So when the zeta is less than 0, it is called as undamped. It's not damped at all. That's why it is called undamped. Underdamped is 0. The value should be within 0 to 1. Then it is underdamped. When it reaches exactly 1, then it is critically damped. If it goes more than 1, it is overdamped. So that most of the systems, as I said, will fall under this category. All the common example systems will come under underdamped systems. Some systems will be critically and some systems will be overdamped. Based on the value of the damping we are selecting out of it, right?
Ma'am, is underdamping possible?
Underdamp is the common, undamp is possible. That's what you are meant to ask.
No, the value of zeta is less than 0, but you
Ah,
told in the second order system that zeta should vary from 0 to 1.
no, 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 no. Okay. Second order system has all these values, can have all these values. It's not like if the system has 0 to 1, then only it's second order. Whatever, if the degree of the system, lowest, highest degree of the system in the denominator is 2, then itself it is second order. We don't differentiate with damping. But I'm telling most of the second order systems will have this kind of damping ratio. Zeta value will come within this 0 to 1. But there are second order system that has zeta less than 0 also. Understood?
Okay.
I'm sorry if I didn't explain it properly before. Okay, now we will see how each damping will look like. For example, this is my output response with respect to time. Then if this is my final value, that is has to be settled, then under dam system would look something like this. It has fewer oscillation, but at last it will settle to the final value. This I'm going to use the red color for under damped. Blue color I'm going to use for critically damped system. Critically damped will exactly have this. It has lesser settling time critically. Over damped system, I am going to use black, where it takes forever to reach the final value, but it reaches the final value. We cannot say it won't. Undamped will be just an oscillation. It keeps on oscillating. We don't know when it is going to settle. That is the undamped system. There will not be any damping to uh, log this oscillation. So it keeps on oscillating. So we are not interested in undamped in any way. Okay. So all we care is this underdamped more compared to other, and critically damped is the best system you would have, but in naturally you won't get to see critically damped system. Exactly one system won't be there, but theoretically we used to study, and overdamped systems are very boring system. It takes a longer time to settle and all. So I will just explain under damped, over damped. Okay, I will not change the order. Critically damped, over damped. Right. As these are all the common thing. Fine. Now, under damped system has zeta. Critically damped has zeta equal to 1. Over damped has zeta equal to zeta greater than 1. So this has peaks, oscillations or transients, and final settling time. Final, finally, it will settle. This has very less peaks, maybe peak nearly equal to 0. It won't overshoot, and it settling time is also less compared to under dam. Even before under dam, this critically dam will get settled. Over dam has settling time very big settling time. It takes very much time to settle, but peak will not be there, overshoot won't be there, equal to 0. There won't be any overshoot. So I would say this is a perfect system, but this is the most common system. Underdamped is the most common system. Overdamped takes forever, and it takes a lot of control effort to make it settle. Fine. Now we are until this point we have assumed that all systems has been settled, right? If it is not settled, then we used to call it as an unstable system. We are not bothered about it. What if I say this is a final value, but it's set in somewhere else? How we are going to call this system? There is a deviation here. It is supposed to settle at the black line, but it is has settled in somewhere else. There is a deviation between that. There comes this steady state error. The steady state error is the difference between final time minus the set point, or final value minus the set point value. So if my final settled value is 1.25, but my set point value is 1, then there is a 0.25 steady state error. If my final value is 0.8, but it is supposed to be settled at 1, then I have minus 0.2 as my steady state error. So this kind of error, we have to again make a control law to make the system to settle at the correct final value. For example, if I put my regulator at 5, even though if I put my regulator at 5, if my fan rotates at 10 rpm, what is the point of using the regulator, right? So I have to replace the regulator so that I will get my desired speed as it is, final speed, maximum speed. So this we used to call it as steady state error. So far we have seen transient behavior and steady state behavior. Right. So in transients, we used to study all this peak time, overshoot, and transient has too many things. But steady state is straightforward. Final versus actual or set point. Right. So this is DD, TS, TD, and everything. We will solve one problem in this, and we will go towards the surprise quiz, and we'll conclude it. Okay. I'll just show you how can we do the steady state error problems. Fine. The question goes like this: what should be the value? Oh, sorry, that's not the question I want to tell. What is the steady state error? I used to call it SSE, steady state error, for a unity negative feedback system with open loop transfer function g of s equal to 20 divided by s plus 1 into s plus 5 when a unit step input is applied. Right. So this is the question where your transfer function of the system is 20 by s plus 1 into s plus 5. From denominator, we know it is a second order system. I am giving an input that is a unit step. Unit step means at 0, it rises to 1 and it remains in that one position forever. So I am getting an output and they are asking for the steady state error. They said the system is settled, but settled somewhere. You have to find the difference between the actual set point and the output you got out of it. With this transfer function, if I give a unit step input, right? Now we have to see what type of system it is. It's a type 0 system or type 1 system. Do you remember the steady state value box? If not, please revisit module 4 of week 4. So there they have mentioned the based on the type of the system, how this will differ. You know what is type, right? Type is the highest degree of the poles at the origin. For example, s power 1, s plus a, and s plus 4, b. This means you have one pole at 0 because s plus 0 here, right? Another pole at minus a, another pole at minus b. So if we have this, then how will you say? For this system, how will you say? You know, you are familiar about poles and zeros?
Yes, ma'am.
Right. So there is again a pole at minus a. This means if I put this in the numerator, right? So
Yes,
like
ma'am.
this, how many poles that are in origin corresponds to your type. So type 0 means there is no pole at origin. Type 1 means one pole at origin. Similarly, it goes n poles at the origin for type n system, that is s power n. So for type 0 system, if I give a step input, I would get a finite value as a output. It's a cheat code kind of table. Okay, for what input, for what type of system, what type of output I will get. Kind of cheat code. So for a ramp input and a parabolic input, these are most common types of input. For ramp input, I will get infinity. For parabola, I will get infinity. And also for type 1, I will get infinity. So here 0 will come like this. Finite will be there in the all the diagonal. But please don't memorize this. Know why it is actually happening, because when you give a type 0 system, for example, it works on the final value theorem, right? I will just brief only one. We'll try to conclude by time. For example, what final value theorem tells you? Why do we use final value theorem?
To check the value at the infinite final time
Hmm.
at t equals to infinity.
Exactly. When t tends to infinity, what is the final value of the system that will be given by this final value theorem? How we will tell this? Limit s tends to infinity. Limit t tends to infinity will become in Laplace in final value theorem. It is limit s tends to infinity s into g of s. This is my final value theorem. If g of I want to find it for the open loop system, if it is g of s, closed loop transfer function, it is c of s by r of s. Generally it will be c of s by r of s. We used to be interested in closed loop systems, right? So based on that, this will change, but the formula remains the same. So if I give a step as an input, for example, limit s tends to 0, s into c of s by r of s if I take. R of s, my step input, where I used to uh, step in time domain is 1, where in step in Laplace domain is 1 by s. Similarly, ramp in time domain is t, here it is 1 by s square. This is t square, this is 1 by s cube, right? So another one we used to call impulse, that this is 1. Okay, fine. So when I give a step input, my RFS actually becomes, ah, why am I writing it? Limit s tends to 0, s into C of s. Some closed loop transfer function is there, divided by 1 by s it will be, right? Here. So based on the type of my system, for example, s into C of s divided by, if my type of my system, that is C of s, is some s plus a, let's take, divided by s into s plus a into s plus b. Already 1 by s is there, so it will be 1 by s. So how this will go? Limit s tends to 0. So this 1s and 1s will get cancelled. When I substitute 0 here, this will goes to infinity, right? So that's how they used to calculate how much type, or for what type of system and what type of input if you have, then how the output will be calculated. If there is no type, if it is a type 0 system, this S in this S will get cancelled and you will get a finite answer. So that's why we got infinite for type 1, sorry, infinite for type 1. Okay, I'm confusing this. Wait. So this is how you used to calculate, right? Based on the type and input of your system, your output will vary. So coming to our question, I will just cut this and keep it here. Okay. Now, tell me if whether this is a type 1 or type 0 system. What is the type of the system generally?
Ma'am, type 2.
How it is type 2? What is the type actually? It's not, order is the highest degree of the denominator. Type is the
2.
highest degree of denominator where the poles are at origin. For example, it should be the highest degree of s. Is there any s termed in the denominator? Not s plus something. Only s.
No, type 0 system.
It's a type 0 because there is no s alone here, right? Based on this, you will find the type of the system. The highest degree of this s will be the type. Highest degree of overall characteristic polynomial of the denominator is your order. Please don't confuse between these two, okay? There is no s term alone, so it's a type 0 system. Type
Okay, ma'am.
0, order 2, right? I hope this is clear. It's a second order system with type 0 characteristics. Now, what is the input you are giving? Unit step input you are giving. So in Laplace, it will be 1 by s. Okay. Now, what is the steady state error? Is the question of the system is the question. So, how will you find the steady state error? Limit s tends to 0, s into g of s, right? So, limit s tends to 0, s into g of s is 20 divided by s plus 1, s plus 5 by 1 by s. So this will be 1 by s is the input. It's g of s in terms of c of s by r of s as I'm considering closed loop system. S into 20 divided by s into s plus 1 into s plus 5. S will get cancelled. Limit s tends to 0. 20 by s plus 1 into s plus 5. This may give me limit s tends to 0. 20 divided by 5. It's 4, right? But E of SS for step input will be 1 by this whole term. For example, if this is Kp, we are calling this as position constant because it is step. Uh, I will explain this if needed. For example, we have this many inputs, right?
Ma'am,
Yeah.
in the upper calculation, 1 by s, that is, then how it is s into 1 by s?
It's like this. For example, A by B divided by C by D. Then it will be A by B into D by C, right? So that's why.
Yes.
It will be 1 by S. Both are in the denominator. So it will be multiplied together.
Okay, 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 okay.
Okay. So these are all the different inputs we used to have, general inputs. So what is the integration in general? Integration is adding terms together, right? Integration can be mimicked into adding things together. So if you integrate impulse, you will get step. If you integrate, for example, impulse is the moment, at that moment, what is the value? That's the impulse, right? At the time steps t equal to 0, what is the value? Then it creates impulse. If I add more impulse like this at every time stamps, it becomes step. So that's why if we integrate impulse, you will get step. So if we again integrate step, if I, for example, if I have one step signal at one time t equal to 0, if it is 2. When t equal to 1, it becomes 2. When t equal to 2, it becomes 3. So if I add these things together, then I will get ramp. So if you integrate step, you will get ramp. If you integrate ramp, you will get parabola. How will you get ramp out of parabola? If this is an integration, this will be differentiation. So if you differentiate parabolic, you will get ramp. Differentiate ramp, you will get step. Differentiate step, you will get impulse. So similarly, if I have a position, for example, I have traveled from my home to Insti campus to 5 kilometer, let's take. So if I integrate this 5 kilometer with respect to the time I have, for example, I spent 20 minutes to reach this campus from home, that is a 5 kilometers. Then I will get at what velocity I have run or what velocity I have rode my vehicle, right? So again, if I integrate this, at what is the acceleration I have given to my vehicle or my foot or my body. So integrating position will give you velocity. Integrating velocity will give you acceleration. That's why when using a step signal, impulse is just a moment behavior. So we cannot realize it, right? When using step, we used to call this as a position error constant. When using ramp, we used to call this as a velocity error constant. Parabola is acceleration error constant. We used to call this Kp, Kv, and Ka. In the presentation, if you see Kp, Kv, Ka, please correlate this with that. Okay. I will conclude it right now. So I will find Kp. So the steady state error would be 1 by Kp, 1 by 4. That will be 0.25 is my steady state value. Right. I'll show you, I'll post a question, just answer this based on this, if you can answer it. Okay. It's a quiz right now. Just answer it in the chat box. Okay. I have it in my desktop, but we don't have time to do it right now. So for under time system, the system keeps on oscillating without any decay in amplitude of oscillations. So the question is example true, B false. The question is under damped system will oscillate like this without any final value. Is it true or false? Just don't answer it. Type it in the chat box. Okay.
Ma'am, show me the question again. Ma'am, where we have to send the.
Chat box. Meet chat box.
You have given mail.
No, no, just wherever you have connected. Gmeet you have connected, no? In that chat box, you put the answer, whether it is true or false. Okay, fine. Okay, everybody has answered. 4, 5, 6, 7, 8 people are there. Please answer quickly. We'll move towards the next. Everybody tells it is false. Is it false? 1, 2, 3, 4, 5, 6, 7, 8. Is everybody answered? Okay. Those who answered lost, I will ask you the question. Nikhil, why do you think it's a false? Nikhil, are you there? Nikhil? Okay. Divyanshu?
Yes, ma'am.
Why do you think it's false?
Ma'am, because underdamped system keeps oscillating without decay.
Okay, fine. Okay, thank you. It's correct. So, undamped systems will oscillate, right? Underdamped systems will have a peak, but still it settles. After some oscillation, it settles. Okay, I'll ask one more question. Oscillation occurs, amplitude will decay exponentially with time. Okay, good. Fine. Now, find the peak overshoot for the system. Quickly find the peak overshoot for the system and type it in chat box. This is the second order transfer function of the system. Compare it, maybe, okay, this is little tough. I will explain it in the next time. Okay, do this. Find the peak overshoot of the system. Put it in the formula, take your calculator and find the value for this. And type it in chat box. Oh, sorry. Okay. What are all your answers? 100%, infinity, 100. So it will be omega n is equal to 5. Zeta will be, how much is zeta? 0, right? So e power minus zeta pi divided by root of 1 minus zeta square it is. So e power 0, 100, right? It's 100, right? 100 is correct. Fine. Please answer the third question. 100 is the right answer. Third is false, false. Please answer also why do you think it's false? In short, whatever you think. We'll conclude with this. The statement is telling as damping ratio zeta increases from 0 to 1, peak overshoot decreases from 0 to 100. Oh, this doesn't make sense. This decreases from 100 to 0, supposed to be. Yeah. Okay. Okay. Right. If someone thinks this is true, tell why it is true also. That's the answer. Everybody answer. Please try type any of the answers. Otherwise, you lose marks in this. I have changed the question. Actually, it was from 0 to 100 before. Just answer it right now. As damping ratio, zeta increases from 0 to 1. Peak overshoot decreases from 100 to 0. True, no. True. Okay. Okay. Please make sure everybody answered. I'm going to cut off. No, it's true. Right. Okay. Okay. Thank you. The peak overshoot formula is e power zeta pi by root of 1 minus zeta square, right? We can analyze this by simply putting zeta equal to 0 to 1. If I put zeta equal to 0, as we did in the last question, it will become 1. That is in percentage, it will become 100 percentage. When zeta keeps increasing 0 to 1, this will tends to 0. E power 0 is
E power 0 is 1.
One.
oh sorry, e power 1 is sorry, e power 1 is e power 0 is 1. That's why we got 100 percentage, right? E power 1 is some random value, right? Minus 1 would be.
But when in denominator, here's the root under root 1 minus zeta square. That is 1 minus 1 is 0. So then denominator is 0. Then e power minus infinity.
Oh, wait. So if I put zeta pi by root of 1 minus zeta square, when I put e power minus 0. When I put 0 here, everything becomes 0, no? There is no point in having 1.
No, ma'am. If zeta is equal to 1,
No, anything by 0 is infinity. 0 by anything is 0, right? It won't be infinity. 0 by 1 is not infinity.
ma'am, I tell when we take zeta is equal to 1, then
Oh, zeta equal to 1. Ah, right. Okay, okay. I thought it's for the previous instance. Okay. When zeta equal to 1, e power minus pi by 0.
then e power
Then
infinity.
e to the power minus infinity, that is
E power minus infinity is
0.
0.
ah,
0.
so it decrease from 100 to 0. That's true, right? When
Yes.
zeta increases from 0 to 1, so the answer is true. Okay. Thank you for joining. And I'll record all these things. You can leave if you want. If you don't have any doubt, you can leave.
Okay, ma'am. Thank you.
Thank you.
Thank you, ma'am.
I'll discuss with professor if we can increase the session. I am not sure about this. And standard degree people used to do one session per week only. But anyway, I'll discuss with sir. Okay.
Ma'am, can you reply our doubts at the discourse?
Ah, okay. I will do
I
it
saw
right
it
away.
is inactive for 1 year.
Right. I'll do it right away. Thank you.
Thank you, ma'am.